In my project, I used trajectory optimization to simulate a squirrel's riding reflex. I was heavily inspired by Mark Rober's video where he built an obstacle course for his backyard squirrels. This included a platform that launched the squirrel into the air if it stayed there for too long, safely of course. Mark Rober was relying on the fact that the squirrel is able to extend and retract its legs and tail in order to change its moment of inertia such that it always lands feet first. I modeled our squirrel friend here as a cylinder body attached to 2 legs and a tail. All 3 joints are actuated with torque limits. The squirrel is allowed to translate in the X and Z axes and rotate about the Y axis. Applying external forces and torques around these axes will simulate the squirrel being launched off from the platform. We can pose the following optimization problem. Given an initial set of external forces, how do we actuate the limbs such that the squirrel begins and lands on its feet? To solve for such a trajectory, I used direct collocation. Essentially, we're approximating the trajectory as a polynomial spline and solving for the control input and state at sample points along the spline. Our optimization goal here is to minimize a set of losses. These have been defined to be the total duration of the trajectory, actuator effort, and the velocity of rotation around the y-axis. I found that penalizing for rotation velocity resulted in a smoother trajectory. The optimization is done under the following constraints. We constrain the range of time between 2 collocation points, system dynamics, initial and final positions, joint position and actuation limits, and the duration and vector values for the external forces applied to the beginning of the trajectory. We run that through a nonlinear solver, and look, our squirrel does in fact land on its feet. Our simulated squirrel first flails, then extends, and lastly retracts its limbs just like the real squirrel. But when we increase the applied external force, we see that the squirrel flips almost all the way around and then flips the opposite direction. That was surprising given that it's inefficient and already constrained for rotation and actuator effort. Future work would be to take a closer look at the costs and constraints to get the squirrel to do a full backflip, or perhaps trying a hybrid model.